Hello. Uh, let's assume you're my client and you asked me to develop an application. So I took few days and deployed it on my server, and you plan to test the application which I built. My single server can handle your request right now, but after few days you thought my application is doing quite well, and you thought of expanding it. So when you plan to expand, you know, there were more requests, and there were more server requests popping on to me, and I decided to build. I decided to add few more servers to the system. Like previously we had one server, and now I plan to have four servers in my system. Now the problem is, how do I handle the load? To which server will I send the request? I need to handle the load unique in a unique way. Each server must take the load by the factor of 1 by n. So how that works, how you handle the load in an efficient way. So when a request ID comes in, you pass it through a hash function which is uniformly random, and you get a code through which you map through that you map to the respective server. So that's quite well for now. So in our present condition, we had four servers right now, and your application is doing really great, and the server's load is getting high. And to increase the system performance, we thought of adding one more server. So we now total have five servers. So previously the load used to be 1 by 25th when we have four servers. Now when we add the fifth server, the load must be equally distributed, and it's going to be 1 by 20, the load factor. So so to mention this, so what happens when you add a new server exactly? The standard way to hash objects. Previously, the standard way to hash objects is to map them to a search space and then transfer the load to the mapped computer. This policy is likely to suffer when new nodes are added or removed from it, uh, because the system totally gets fumbled up. What's the cost if the system gets fumbled up? We are adding a new server and system is getting faster. You might have a doubt like that, but each request we get is not totally random. There are users who repeatedly hit our servers. So based on the user, we store their personal information on the servers in the local cache, so that the system need not hit the database repeatedly. So you can't fumble the system which stores the local cache. So once you add a new server, you can't afford to do that. So what we can do is we need to make sure there is a minimum disruption in the system. So what we can do is we can plan to add virtual nodes. What I mean is, like, see, let's suppose all the request IDs in the hash ring having hash value greater than s naught, the first server, are to be served by s1, and the request IDs greater than hash of s1 are to be served by s2, and so on. This continues, and the difference between these servers might not be the same, which means a server might end up serving more requests than one another. So when we increase the number of replicas to k points, the chances of node on each virtual point is less. Half the load, there might be instances where half the load is on a single server. So we can avoid that. That's what chord exactly does. Chord is basically based on consistent hashing, which we discussed right now. So chord is a protocol and algorithm for a peer-to-peer distributed hash table. A distributed hash table stores key value pairs by assigning keys to different nodes. A node will store the values for all keys for which it is responsible. Chord even specifies how keys are assigned to nodes, and how a node can discover the value for a given key by first locating the node responsible for that key. uh, mm, you know uh, let's say how does chord how chord does that. Uh, you know let's assume the basic approach is to pass the query to a node successor. If it cannot find the key locally, this will lead to a linear time, O of n, where n is the number of machines. It costs the system a lot, so we need to improve the lookup. How can we do that? So if the id falls between n and successor of n, successor n is written. Otherwise, lookup is performed at node n, which is the node in the finger table of n that most immediately precedes id. Since each node has finger entries, the finger table which we maintain, the main purpose of this is to make the system efficient, to make the lookup improved. uh, so uh, so each node has finger entries at power of 2 intervals around the circle, as you can see there. Each node can forward a query at least halfway along the remaining distance between the node and the target. So here the runtime is logarithmic to the previously compared, which is linear, which really caused the system. In the chord system, when a node joins, I basically implemented using Java. When a node joins, I made sure it calls the join function. The node n asks n to find the successor. Uh, you know, it asks whether it already exists or not. It looks for n in the ring. So on each addition and removal of nodes in the ring, I made sure I stabilize the system uh, through the stabilize function which I used. So what it does, um, the stabilize function in which n asks its successor for its predecessor p. That's what it does, and it notifies. There's a function called notify which notifies n's successor of its existence, so it can change its predecessor to n. And I'm even making sure I update the finger type tables. That's how your data can be consistent. And now let's take a look at the example. um, let's have a look at the example. Let's say now here we are in the search pair of identifier space of M5. So we have 30 nodes, 32 nodes. So these are the nodes which are disabled, and we have only these nodes which are enabled on the ring. So we got a query right now. So we need to look up k is equal to 26 in its finger table on node n, on node 1. Let's assume it's on node 1. So what happens? The value of k is 26. So what node 1 does, it searches. So the highest predecessor is 18. So it forwards the request to node 18. Node 18, uh, it doesn't find 26, but it forwards the request to node 20. It still can't find 26. It forwards the request to 21, and then to 28. That's where 26 resides. So at that point, the address of node 28 is returned to node 1. So that's how a query system in Quad works. So what happens, when like lookup might fight lookup might lookup the lookup which we do, it might fail if the successor pointers are not up to date, you know, as soon as the successor pointers are correct, only then the lookup will work. Over time finger tables will be up to date. We need to make sure, I just made sure the finger tables and the stabilize functions is getting called at a certain rate. Only then the data is consistent here. uh, so yeah, thank you.